humans are always better when they think outside the box. And that's how we are here, in terms of innovation.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Technological advances are transforming manufacturing industries, promising more dynamic and efficient products that improve people's lives, strengthen the national economy, create higher-paying jobs, and enhance U.S. competitiveness on a global stage. Materials scientists are developing new materials with advanced properties to meet the moment. We're joined by Kieran Solanki, a professor of mechanical and aerospace engineering at Arizona State University. His team specializes in designing new materials and enhancing existing ones for extreme condition applications in the aerospace, energy, and defense industries. Professor Solanki, thank you so much for joining me today.
Hey, thanks, Nate. Thanks for having me. I appreciate the opportunity to present what we have, and it's great to talk to you.
I think for the first question, we need to do a little bit of terminology setup here. And for people that don't really know, what are super alloys? And maybe you need to start with what's an alloy to me, like in general.
So anytime when you try to mix two compounds together, whether A and B, you're trying to mix them together, it becomes an alloy, right? So like, for example, if you're trying to mix oil and water together, it becomes not a water, it's not an oil, it's an oil and water together, it's a mix. That's what an alloy is. An alloy typically referred to mostly on the metal side. So you take iron and you add, magnesium to it, and then this becomes an iron magnesium alloy. Going back to your question about superalloy terms comes from the foundation where the metallic alloys are engineered to have both strength and stability. When I talk about stability is the temperature stability. So when you try to heat up something, it needs to stable so that you can operate at those temperature. They have internal microstructure. So like we have internal organs that operates, and that's how we work. Same way the material has its internal constitution, internal microstructure that works together to give you the properties that you want at the macroscopic level where you are working with it, right? So the internal microstructure is unique, and that gives you high temperature. They can absorb a lot of mechanical stress. They can operate in a corrosive environment such as jet engine environment where you have temperature, gas, and things like that. So traditionally, you use nickel-based alloy. Now we are changing the game by introducing copper-based alloy. Because they have unique advantage. They have specifically electrical and thermal conductivities are pretty high. So think about it that if you want your material to work at higher temperature, you want that material to cool down faster, right? So thermal conductivity plays an important role. So you can use those material, that aspect of it.
Thinking about the paper that we're or this particular bit of research that we're looking at, when you went to replace the nickel with copper, how much was that really in front of mind, the characteristics of copper versus the characteristics of nickel? Was it more of an experimenting with different kinds of metals and you arrived where you arrived, or did you know you wanted to try this out?
So like I said, that, everything that leave behind has a fingerprint. So when a material operates at very high temperature, we know what are the fingerprints that nickel has. Nickel superalloys dominates the aerospace and turbine application. So jet engines and all kind of outer space application, aviations and things like that, nickel-based superalloys dominate, but they are less conductive. Okay, and so what you want to do is you want to replace with a material that has a more conductivity aspect of it, right? So we introduce copper tantalum, which is a copper with tantalum, and copper tantalum with a little bit of lithium, like a 0.5 atomic percent of lithium, which is a minute compared to anything else. Okay, it's a minuscule. All right, the idea is that they have a high strength, but also have the electrical and thermal conductivity that makes it ideal for next generation of electronics, hypersonic, nuclear application with heat dissipations and durability matters. So it's not just the strength, but it also provides the heat dissipation aspect of it. And copper is well known in that aspect of it. But the copper suffers where one point is that it is looked down because it's a very soft material. Okay, so it looks down, and our objective was to make it stronger. Yeah, bring it to the big league rather than
Right.
having
So
it.
it might be less obvious plate to start from.
Sure.
So how important is the crystalline structure that you have?
The crystalline structure is important. If you're talking about nanocrystalline structure, so for audience, nanocrystalline structure means that you have a grain, which is a smaller pancake within the material, to be in the order of 100 nanometers. Think about, hair size is a micron, right, in diameter. So the grain size of a pancake within the material is very, very small. You need a transmission electron microscope to see it. You cannot see it with the naked eye. Or what happens with those pancakes, right? Think about is that if you have one pancake, but then if you have thousands of pancake together and you try to push them together, they become harder as compared to individual pancake, right? Or again, essentially. So having a nanocrystalline, which grains are just a billionth of meter wide, billionth of meter wide, dramatically improves the strength and wear. But they are very, very unstable. They are like notorious children. Okay, they just want to run around. Okay, and they want to expand, and so you want them to be stable. And that's why we created a copper tandem system, which is finer in structure but more stable, that provides the strength and ductility and heat dissipation mechanism at the higher scale. So traditionally, if you have grains which are billionth of meter wide, they are unstable, so they don't get utilized. And what we are trying to do is we are trying to utilize those properties, but making them stable. Okay, sort of an order structure.
And for your testing, you had this material be durable for a very long time in a very extreme environment. Can you talk a little bit about that bit of the research?
So the idea is that you don't want to, develop a material for the sake of a material, right? I mean, I can take a recipe and modify a recipe to just make a better tiramisu, right? But I want to create a deconstructed tiramisu in such a way that I create a new dish. And in that sense, from that analogy point of view, think about having a material that can not just withstand small amount of temperature or small duration of time, but a longer duration of time. And the idea is that you want to expose them to an extreme environment, because think about it, heat of a supersonic flight, a deep space radiation, or corrosive nuclear reactor, these are all our extreme environment. And if we have to move towards that area in the next century, and it is important for us to think outside the box and bring them into a picture, right? So that's why we subjected these alloy to not just a normal working temperature, but extended period of time at the higher temperature. Durability is not a luxury; it's a mission, which is critical, and that's why we subject them to extreme temperature and duration.
Right. It was something like a year you had it under
Yeah,
that
over the
temperature.
year. I mean, why not, right? Why not? I mean, used to be that people used to do research and tend to do the research over a long period of time before they would present. Now everybody wants to cut that duration because of all the pushes that we get around. So it's important to take a step backward and really think what is the right way to, not just a right way, but what is the critical important information that you want to give out to your audience. And that creates the stage, right? We could have published this paper 3 years ago if we didn't want to do these kind of research, but we wanted to see how extreme or how far we can go. But one should not stop. That's what the curiosity is. That's what it drives. And that's why it motivates us to do what we do.
And I think it's a little bit of a proof of concept when you have it for that long that it could be in space conditions, say.
Yes. So one thing that we always think about is that how you do a translation, right? Or translation of research. And translation of research require proof of concept over not just a short period of time, a long period of time. And that's what the industry prefer. When they want to qualify a part for a fighter aircraft or anything, it takes long period of time for them to qualify, and we are trying to help that bridge the gap by telling them ahead of time that, hey, it will work, and here is the proof.
You mentioned that you know what different aspects of different metals or different chemicals. As you're trying to design more resilient materials, what are the challenges in that design process?
To answer that question, you would take a step backward, why there is a Marvel team, not just one Marvel character, right? There is a team. The idea is that you want to have different aspect of the team to play a role, whether it's a Captain America or Iron Man. You want all of them to be part of a team to be a successful mission. In the same thing, when you're trying to develop a material, you want competing properties to be optimized. Okay, strength and ductility, conductivity and stability. These are all conflicting properties. You want them to come together as a synergistic way. That way, it helps not only to be able to apply that material to new application, but also think about how we can generate new advanced material. And so we use tools like, alloy design, thermomechanical processing, advanced simulation to engineer that balance, okay? And bring that together, often pushing the boundary of what physically not possible or physically possible, right? We're trying to push that boundaries. Just because we have an equilibrium state and status quo doesn't mean we cannot push. And that's what the scientist's curiosity comes into play. And my objective and my way of thinking is that what's next? What is the thing that I don't know? That's what drives me. Okay, and that's how it is. Whether it's in a relationship, whether it's in a family life orientation, whether it's in the scientific community, this is what drives me. What I don't know, right? And that curiosity of knowing, that the curiosity that you don't know certain thing, right? And you don't know. And how do you decipher that?
You mentioned some of the uses this could potentially have. What is the path to getting this into, say, aerospace technology?
Think about extreme tech, okay? Right? Extreme techs like hypersonic aircraft, people are, talking about it, or space travel, space propulsion, nuclear fusion reactor, or high temperature, high performance electronics, right? Or even simply thinking about how to generate next generation of frying pan, okay, that are optimum from a green energy point of view, right? And so you need materials that are not only can take the mechanical, but thermal load together, right? And so having these kind of research where you can show the long-term duration gives you the proof of concept. Then working with industry, partner industry and government affiliation, and trying to come up with how do we qualify these parts. Because remember, everything that happens in the lab doesn't get translated, but when all the community comes together, then it makes it easier for us to translate that research into a component or application or a product, and in a sustainable way.
Are there challenges potentially scaling this technology with having access to copper?
I think we have abandoned the mines. Obviously, there are resourceful. The resource that we have, we need to use it very effectively. We don't want to, overdrain ourselves and things like that. So, state of Arizona, where I'm from, Arizona State University, the copper mine is everywhere. From a copper producing state. There is abundance of copper and there is always a discovery of new mines everywhere, but obviously utilizing them effectively, right? So the idea is that you make them such a strong material that you utilize them low in volume. So instead of using a brick, you use a small plate. Do you understand what I'm trying to say? So the volume shrinks down to smaller because the strength is pretty high. Right. And so that's the whole idea. There is always a trade-off between strength, amount of material that you have, what you can use, and how much reliance on the foreign government countries and things like that, where we can procure these kind of aspect of it. So there is always a balance. And so that's why, trying to avoid certain type of rare earth material, certain types of material that are, very difficult to mine, right? Would be the way forward when we are designing the material. You have to look at those constraints. And hopefully one day we can translate the material directly from the extraction site to into a finished product with some sort of chemical processing and other types of technique where you don't have to have so many different places where you need to use logistically, spread across the country. You just go directly from mine to a finished product. Hopefully one day that will arrive, and that's the challenge, the biggest challenge for the next generation.
I want to ask you about funding a little bit. Can you talk about how NSF support has impacted your career so far?
It's a great question. It's in a great time. The one word is freedom of innovation. That's the key sentence that I would want to portray is that freedom of innovation. NSF support has been foundational, not just for me, across everybody, across the United States. It allows to explore high risk, high reward. And I'm talking not just based on my personal experience as a professor, but I'm talking when I was a grad student, when I'm undergraduate student, the curiosity. I'm an immigrant. I came from a country I came from India, right? And I looked at NSF as a pillar, right? If I can get funded from NSF, then basically means that my research is basic. My research is high risk, high reward concept, right? Such as this nanocrystalline copper alloy or integrating AI for materials discovery. Those funding, you wouldn't touch, no other traditional funding mechanism won't touch that. Okay. And so it's not just funding, it's about freedom to innovate. And that's the most important, sentence. It's freedom to innovate. And that's what allows NSF funding project for us to be able to do what you are then, and gives us opportunity to talk to you.
For the last question here, I want to end with talking to you about the future and what's next in your work. Where would you like to see Alloys going in the next few years?
What I want to do is to be able to think people about all the fingerprints. So if something breaks, it leaves beyond fingerprint, right? And those fingerprints people can understand, or research and scientific community can understand. We do understand. And we want to reverse engineer those by understanding those fingerprints. And we need to think about from a non-equilibrium processing, not in an equilibrium. Equilibrium means it's stable. So if I let the water and oil and try to mix them together, after 5 minutes, they separate out, right? They don't mix together. But if I agitate them continuously, they will be not in a stable structure form. They will be continuously trying to mix together. Whether they can mix or not, that's a different story. But you want that as a non-equilibrium processor is to keep developing and pushing by understanding the fingerprint and not stopping at that, by seeing, okay, can I use non-equilibrium to capture those fingerprints that left behind and eliminate those fingerprints such a way that I can make material more durable. I'll give you an example. Can we produce hydrogen through electrolysis process using aluminum as a base powder? And RV is working on it. There are other funded agencies that are looking at interested in developing a structure that can actually produce hydrogen from any water source, whether it's a Gatorade or whether it's a dirty water. It can produce hydrogen, and that basically allows us to run critical structures in a mission-oriented stuff, or provide support to a rural area where you don't have electricity. It can also helps you in a water purification aspect of it, where you have water. So now we need to think about is how do we make these structures, not just copper tantalum alloy, but other kind of structures or other alloys that helps build sustainable environment and sustainable infrastructure where resources may be limited, where you need, where you don't have, where the resources are limited and we can provide them effectively, to help alleviate the problem that they may have. For example, state of Arizona, water is an issue, right? So we are thinking about how we can use this material, these type of material, to make water purification, water harvesting better, things like that. The one thing that I want to give an importance is that knowing what you don't know is an important driving force. And freedom of innovation comes to agencies like National Science Foundation, and supporting research of mine and other people is critical. And that's the take-home message is that who I am it's not just because of my mom, dad's, and my family's training, which is important, but also as a scientifically career point of view, having a funding agency such as National Science Foundation and other government agency is important for us to think outside the box, because humans are always better when they think outside the box, and that's how we are here, in terms of innovation.
Special thanks to Kieran Solanki. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.